All right, so the job is to debate the question of whether or not general relativity or quantum mechanics is more fundamental. It's not necessarily obvious what that means, not obvious to me. I take it to mean something like we both believe, some of us believe, that there is a correct theory of the world, and when we find it, that theory will reproduce the empirical successes of both general relativity and quantum mechanics in the appropriate regimes. And the question of fundamentalness then might be taken to ask, will that theory sort of keep the fundamental structure of quantum mechanics exactly intact and general relativity will be emergent from that? Or will the basic principles of GR be right there front and center and quantum mechanics is somehow shunted off into a corner? Clearly we don't know the answer. So a matter of taste is involved, many matters of taste, and we'll have to see, unless a retrocausal person in the room can tell us what the final answer is going to be. But I'm on the side of quantum mechanics being more fundamental. That's not because I don't like general relativity. I wrote a book on it. You can all buy it. General relativity is awesome. I said in the book, and I still think it is the most beautiful physical theory ever invented. But in the contest between general relativity and quantum mechanics, it's not a fair fight, right? My side is sort of the obvious, straightforward choice in the debate. Which does not mean it's right. I'm actually not making a value judgment yet. I'm not making an argument yet. I'm just saying that that what happened in physics is there was everything that happened before Isaac Newton, and then there was classical mechanics, and then there was quantum mechanics. These are the three phases of the history of physics. And general relativity is a classical theory. It's a classical field theory. There is a degree of freedom. There's the metric tensor field all over space-time. You can write it in a phase space formulation with a conjugate momentum. Observables are every function of phase space you can imagine, and all the apparatus of classical mechanics just with this particular Hamiltonian or Lagrangian. Whereas quantum mechanics says the world is an entirely different thing. There's the uncertainty principle. Rather than phase space, we have Hilbert space, and so forth. When you were faced with any other classical theory of the world, you would quantize it. And there wouldn't be a battle between that classical theory and quantum mechanics. It would be subsumed. So the question is, why would you not think that that was true about general relativity? And the answer, I think, well, for one thing, there's two answers. The very short answer is it would be hard to see... No, sorry. I need to add one more point to why it's obviously true that general relativity is less fundamental, because it's hard to imagine how it could be more fundamental. General relativity gives you an equation, Einstein's equation with the Einstein tensor on the left-hand side and the energy momentum tensor on the right-hand side. General relativity being more fundamental would somehow mean there was a classical space-time metric that still obeyed that equation, and it's utterly unclear what the right-hand side should be, what the source of gravity would be if the metric were left classical somehow, if the metric were not straightforwardly quantized. If you had a source that was in a superposition, a macroscopic object in a superposition of two different positions, where's the gravitational field pointing? Is it in between? Is it to one or the other? You would have to, in order to make that work, you would have to imagine some modification of quantum mechanics that made every macroscopic superposition collapse very quickly, so there weren't any macroscopic superpositions of matter and energy. And maybe you could do that, but it's not at all obvious how it would. Okay, so why would you ever want to do something like that? I think we all know the answer to that, which is that when you try to quantize gravity, all hell breaks loose. Steve Carlett gave us a nice talk on how you can do it in this extraordinarily special case of 2 + 1 dimensions without any matter or anything like that. But more generally, it's hard. And it's hard for 3 different sets of reasons. Number 1, the technical reasons. It's not a renormalizable theory. Everything is infinite. It's hard to make predictions. Number 2, there are conceptual difficulties. The nature of time, and especially the nature of space, is actually a big problem, right? The idea of a local observable doesn't seem to exist in general relativity, because if you imagine that the metric itself takes on different possible values, let's say on different branches of the wave function in Everettian language, it's hard to say that to identify the same point in 2 different branches of the wave function. So what is locality even supposed to mean? And finally, there are what we might call the visceral objections to general relativity being quantized. We think of space-time as the arena in which things happen. This is clearly how Einstein thought. You know, Einstein really had trouble wrapping his mind around the idea that space-time was anything other than the arena. And naively, if you quantize general relativity, space-time is not that fundamental. At least the geometry of space-time is not that fundamental. Now, I would argue that that's not an especially good argument. I would argue that any quantum theory devalues space-time as the arena in which things take place, because once you invent entanglement, you know that it's more like configuration space or momentum space or some other polarization of space. And I would further argue that if you really like and honor the values of quantum mechanics, you forget about space-time altogether. Quantum states live in Hilbert space. They're vectors in a vector space, and Hilbert space is where things happen, and everything else is just a useful way of talking. So this attitude is something that my collaborators and I have taken to extremes in something we call the Mad Dog version of Everettian quantum mechanics. Mad Dog because many Everettians still held themselves to a notion of what the fundamental variables of the theory are. You're quantizing the electromagnetic field and the Dirac field or something like that. I think that's cheating. I think we know plenty of examples where there's two different classical variables and two different classical theories which you quantize and get the same quantum theory. Quantum theory should be thought of as a theory that describes vectors in Hilbert space, and the right classical way to describe it needs to emerge. So that's what we're working on. So even space-time has to emerge. And the good news is you can kind of see the outline of that, how that happens. For a generic Hamiltonian, you wouldn't expect any local space-time description. But for very special Hamiltonians, there is a local space-time description, and when there is more or less unique. And you can take that space-time description just based on the Hamiltonian, just based on the spectrum, the eigenvalues of the Hamiltonian. And you can say that if I had a state in that Hamiltonian, a low-lying state near the vacuum, I can use the entanglement structure of that state to define a metric on space and perhaps on space-time. And I can even argue that there's an equation that that metric obeys, and that equation looks exactly like Einstein's equation. So this is very speculative. We're nowhere near filling in all the blanks, but it seems at least plausible that rather than quantizing gravity, you can find gravity within quantum mechanics. Given the right Hamiltonian and the right state, you see that at the level of the semi-classical approximation, what is being described are some fields propagating on a background metric. I think that's a very satisfying way of doing things. There's plenty of problems with this. The biggest single problem is that we deal with locally finite dimensional Hilbert spaces, which makes it very difficult to implement things like Lorentz invariance and diffeomorphism invariance, etc. So we say, guess what? Those are not fundamental. They are emergent. That may or may not work. This is what we're trying to do. So basically, we are making all the visceral problems of quantizing gravity harder. We're facing up to them by saying they weren't problems at all, you gotta suck it up, okay? So this goes very much hand in hand with what I think is, just to sort of finish up this little rant, why do some people think quantum mechanics is more fundamental and why other people think general relativity is more fundamental? There is just as much of a matter of taste here as a matter of physics, because you have to give up something, and the question is, what are you going to give up, right? Which of your cherished beliefs or your fundamental principles are going to have to go? And I remember vividly Lee Smolin pointing out to me that there was a strong correlation between people who believed in the Everett interpretation of quantum mechanics and people who thought that computers could someday be conscious. And you wouldn't expect, these are two very different kinds of questions, right? But it's the same people who line up. And if you believe in Everett, you also believe that AI can become conscious. Why is that? Well, I think that there's an explanation. It depends on what you value. If you're an Everettian, you've learned to accept what you value are very, very simple fundamental principles. And what you give up on is a very short, direct connection to the underlying fundamental theory and the world of our experience. There might be many layers and many different kinds of emergence and a lot of project and work, full employment to be done in relating the simple underlying principles to the world that we see. And that same kind of cast of mind lets you think, I don't really know what consciousness is, but I don't see why a computer can't do it just as well as a person. Where there's another cast of mind that says consciousness is something that I'm feeling in my brain, I can't even imagine a computer doing it. Tables and chairs are something I see, they're located in space-time, I don't want to give up on them as fundamental things. I don't know which one is right, but I think for the very same reasons that I think that Everett is a good formulation of quantum mechanics, that in the battle between general relativity and quantum mechanics, general relativity is going to be the one that ends up more fundamental. Quantum mechanics, damn it, making his case for it. Quantum mechanics,
right to the end.
Licensed quantum mechanic. I have the license.
Living patternist.
Yes.
Now we'll go to the other end of the debate bench.
Okay.
The debate bench.
Yes, the debate bench.
Well, first thing I want to say is that, before I get into trying to defend Einstein, I do think that the kind of work that I do think that the kind of project that Sean is talking about is the most valuable kind of project that we have in the foundations of quantum mechanics, which is, I don't think that we can resolve the problem of the interpretation of quantum mechanics without trying to push these ideas into new physics. Right? So if Mad Dog Everettianism turns out to be right, and Sean has the correct account of the emergence of space-time and the emergence of gravity, then it will be very difficult to argue that the Everettian point of view is wrong. And so this is precisely the kind of work we should be doing. However, what I disagree on is how this is going to play out. So the first thing is, as Sean mentioned, we have to interpret what the question, which is more fundamental, quantum or general relativity, means. So the way I interpret this question is possibly a bit different. I'm not thinking that we're going to end up with a theory which has a classical metric. What we all agree on is that the fundamental theory, whatever it is, has to, in the appropriate limit, give us general relativity and give us quantum field theory in the standard model, right? So if you want to call that theory quantum gravity, fine. It may not turn out to be a quantum theory or recognizable as a straightforward gravity theory, but it's some theory which has those things as its limit. So the way I interpret the question is, in that theory, will I recognize principles that come from general relativity as being its foundation, or will I recognize principles that come from quantum mechanics as being its foundation, which are more likely to be reliable? Okay, so I want to give two arguments for thinking of principles from relativity as being more fundamental. The first one is, I think, a fairly solid argument that, as somebody who spends time thinking about quantum foundations, I definitely stand by. In the second argument, I'm going to go way out of my comfort zone and be very speculative and talk about things I don't know very much about. So let's start with that. So the first thing is, when I think about, will this fundamental theory, what kinds of principles will it have? Will it have principles from quantum mechanics or principles from general relativity, or both? When I think about the possibility of it having principles from general relativity, I think it's very clear what those are. Or at least you can list some things that are important in general relativity. For example, the idea that gravity reduces to geometry, the idea that the equivalence principle, that gravity is equivalent to acceleration in a certain sense. I wrote down a few more here, I'm sure. Can't remember what they were. Let's see. Yes, equivalence of different coordinate systems, that the laws of physics shouldn't depend on your coordinate system, etc. So you can write down these things and it's sort of clear what they mean. And it's clear what they mean independent of the mathematical framework too. Well, of course, if I'm going to talk about gravity being geometry, I have to be talking about some sort of geometry. But it doesn't have to be Riemannian, pseudo-Riemannian geometry, right? If I formulate a discrete geometry, I can talk about what it would mean to have a coordinate-independent theory in that geometry. Or if I even formulate a non-commutative geometry, I can talk about what those principles would mean for that geometry. They are principles which are broader than the specific mathematical framework of differential geometry that general relativity is usually formulated in. So although the details of doing these things are indeed extremely tricky, right? To talk about what do you mean by Lorentz or diffeomorphism and invariance in a discrete geometry is a very difficult thing. But nonetheless, I can think about what those things mean and it seems to make sense. On the other hand, what principles is quantum theory based on? There are things that we tell undergraduates they're based on. We say the uncertainty principle is very fundamental, but I can't get anywhere near deriving the mathematical formalism of quantum theory from that. And also, when you talk to different physicists, they will give you a different list of things that are the principles of quantum theory. So some might say, oh, it's the canonical commutation relations, or it's the Schrödinger equation, or it's the structure of Hilbert space. All of these things are posited as fundamental principles of quantum theory, but they are, number one, very different depending on who you talk to, and number two, usually very closely tied to the mathematical formalism, right? So if I say this fundamental theory is going to be somehow quantum-like, does that mean it has to be formulated in Hilbert space? It's difficult to say. So since possibly, I mean, there's more agreement in this room than in general, but generally speaking, I find it hard to understand what even the principles of quantum theory that are supposed to be preserved in this theory are, right? So I think if I'm asking myself which of those two sets of principles are more reliable as a guide to constructing this theory, I'm going to choose the ones which I can understand what they mean in a broader framework. So that's the first argument. So for those reasons, I think general relativistic principles are more reliable guides to theory construction. In the second argument, I'm going to get a bit speculative. I'm willing to defend the idea or make the prediction that quantum theory will be long gone before we get to the scale of quantum gravity. So I have to give some reasons.
You're being
for
recorded, yeah.
I know. So there are, of course, people who believe that quantum theory will break down for various reasons. Usually the reason is they want to solve the measurement problem. So if you think about the spontaneous collapse theory, for instance, there will be some size of macroscopic system at which the rules of quantum theory break down, and we'll have a different theory. Now, I don't think that's the reason that quantum theory will break down. I think that it may get replaced by a theory that's even weirder than quantum theory. I don't think it's going to break down in order to solve the measurement problem. But what I do think is that there's an awfully large number of orders of magnitude between the scale at which we know quantum theory and quantum field theory works and the Planck scale, right? So it's quite, to think that our physical framework won't break down before we get there is quite an extrapolation. Specifically, there are problems in quantum field theories in high energy physics that occur before we even get to the Planck scale. So this I have to start looking at my notes for. So, for instance, the grand unification scale is believed to be about 3 orders of magnitude smaller than the Planck scale, so about 10 to 25 electron volts versus 10 to 28 for the Planck scale. As of now, the best bet for unification, grand unified theories of the three forces have been supersymmetric theories in which the coupling constants are supposed to run together at that kind of value. All evidence that we have so far suggests that those theories aren't the right theories. Like the LHC has not found any evidence for supersymmetry at this point. So right now we're in a limbo where we don't even know really how grand unification is going to work for the other three forces, let alone gravity. Now, 3 orders of magnitude might not seem that much, so it might be that there are effects that come from the Planck scale that affect that scale of physics, but it's still quite a large number. There's quite a large difference. There could be new physics that comes in at that scale that doesn't have anything to do with Planck scale physics. And so high energy physicists have got really great at model building, trying different kinds of symmetry groups, trying different kinds of ideas, but they're all formulated within quantum field theory. Like nobody has posited a model that isn't quantum theoretic in order to try and solve these problems. So what I'm suggesting is that maybe there will be a theory that reduces to quantum theory appropriately, but is somehow more general, that comes in somewhere around this scale, and that by the time we get to quantizing gravity, maybe we don't have something that's recognizable as quantum theory after all. So, let me give a very, very, because I'm not an expert in this area, but I'll give you an idea for an idea. So in the foundations of quantum mechanics, we have studied theories that are more general than quantum theory, specifically in the framework of generalized probabilistic theories within the last few decades. One of the things that you find in those theories is that the structure of the state spaces can be very different from a Hilbert space, and in particular, the way the relationships between numbers of parameters work can be different. So you can talk about the number of states that can be perfectly distinguished in a theory, that's some number, let's call it D, and you can talk about the number of parameters required to specify a state of the theory, let's call that number N. In quantum theory, you have the relationship N equals D squared, but you can have theories in which this is very different. Now, N is basically the dimension of the vector space in which your theory lives. So the thing is, one of the things that you need when you're building a grand unified theory is you need a space in which a representation of your grand unified symmetry group is going to act. If you assume standard Hilbert space quantum mechanics, you are restricted to talking about unitary representations on the Hilbert space. If we started talking about representations of groups on these more general spaces, we could have indeed more parameters to play with, more different kinds of representations that we could try and look at. And maybe, this is extremely speculative, but maybe you could get some kind of unification without needing supersymmetry, or maybe you could make a prediction which could be verified in the near term. So that's just one speculative idea, extremely speculative, but I think the general point is that there's a large number of order of magnitude still to go. The idea of modifying quantum theory in order to solve these kinds of problems hasn't really been tried because the people who've been trying to understand those kinds of theories haven't come at it from a sort of foundational background where modifying quantum theory is even on the table. So if I'm going to make a prediction, I think the principles of general relativity will survive up until that scale, but the principles of quantum theory, if we can even agree what they are, won't necessarily survive. I don't think they're a reliable guide for theory building.
Can I briefly respond before we open it up? So I actually think in your second point, where you point out that there are things we don't understand yet, and exploring the possibility of modifying quantum mechanics might be a sensible strategy, I agree with the motivation. I think that modifying quantum mechanics is probably a long-shot strategy, but that's in some extent a matter of taste. I do think that modifying quantum field theory makes perfect sense, because many of these problems are up near where gravity becomes important and quantum mechanical. And if I'm right about the finiteness of the Hilbert space that describes local regions of space-time in quantum gravity, then quantum field theory is going to give out. It might give out long before you reach the Planck scale, even though it's still fully
QFT will give out.
QFT.
Yeah.
Right? If I had too many glasses of wine, I'm not really drinking.
No, but that was just clear.
Yeah, quantum field theory, QFT, will give out, but quantum mechanics, I think, could still be perfectly valid to address some of these questions. To your first point, yes and no. I mean, certainly at face value, the principles of general relativity, which is part of the fact that it's the most beautiful physical theory, are crystal clear. We all agree on them. There are not big debates on the interpretations of general relativity. The principles of quantum mechanics, as you point out, there's not a consensus on what they are, but there are options for what they might be. And I would say that if any one of those options, whether it is some Bohmian view or many worlds or GRW or something epistemic, if that's what turns out to be right in the ultimate unification of quantum mechanics and gravity, I would still declare victory in the debate today. Certainly if it does turn out to be an Everettian point of view, then I would declare victory. But I would ask, the real point I'm getting to is that you say correctly that in GR we have a geometry. You could imagine that a better theory of gravity, it might not be the pseudo-Riemannian geometry that we have in general relativity. 100% open to that. That's very interesting. I've tried it myself. But do I take from that the implication that you think there will be a geometry rather than a wave function of geometries or a superposition of geometries?
Well, I mean, I don't know what they'll be ultimately. I mean,
Neither do I.
I am a psi epistemicist, so I don't think that the wave function on Hilbert space or quantum states on Hilbert space is fundamental in any sense, right? So this is one sense in which I think, you know, if this kind of view is right, and I develop this, say, psi epistemic view into a full interpretation of quantum mechanics, and then I say, okay, what does that mean for gravity? Then the result of that, I think, might not be recognizable as something that you'd want to call a quantum theory, because I'm going to say the fundamental degrees of freedom are. I mean, I may end up using more or less none of the mathematical structure of quantum theory in that theory. So I'm not. I mean, I guess it's a question of terminology, but I'm not sure that if I accomplish that goal, you really would say that thing that you've derived is recognizable as a quantum theory in some sense. So it's not clear. I would also say to the other point, you know, we do have, you know, at least half a dozen interpretations of quantum theory that work. I don't think we have half a dozen different sets of principles underlying quantum theory that work, because the way that most interpretations work is that they take the mathematical formalism of quantum theory at sort of face value as at least most realist interpretations take it as at face value as representing, you know, we don't need to have another derivation of the Schrödinger equation from some principles, for instance. We take that mathematical formalism as at face value, and then we either add things to it or we try to interpret it as it is. We don't try to, in general, formulate our foundations of quantum mechanics in terms of physical principles like the ones in terms of general relativity. So even if Bohmian mechanics turns out to be right, I think it'd still be sort of hard pressed to say exactly what the principles of quantum theory are in a way that everybody would agree, in a way that would be non-controversial to the same extent that you would in general relativity. So it's not sort of a question of maybe one interpretation's right and another one's wrong. What I'm trying to point to is that, you know, there don't seem to be these sort of well-founded principles that we could get any kind of consensus on.
I just want to be on the record as saying that it makes me very sad that I am on the stuffy conservative side of the debate. I would much rather be the radical bomb thrower, but conscience forbids me in this particular case.
Both of you guys.
So, can we open a door? It's getting very warm in here.
Yeah.
I agree. I think it's too loud.
Okay.
So, there are noble arguments on your side.
What?
And
And I appreciate this, but I can't help but be attracted to Sean's side of this particular debate. And I think that there's another type of argument to throw in. General relativity has this attraction, how clear it is, how the beauty of it, the elegance is, as it's been suggested. Quantum mechanics has a kind of generality that general relativity doesn't. In some sense, general relativity is a very special theory. It's a theory of a special kind of field. Important, especially since it gives us the structure of space-time. But quantum mechanics at least purports to be the theory of all properties, all possible observations, and the statistical properties of those properties and observations. I don't think we should allow the difficulty of making sense of quantum mechanics undermine our sense of its primary importance to physics. I think if there's a candidate theory for foundation, it has to be quantum mechanics. Now, what are the quantum principles? I don't know. That's part of why it's hard.
right.
There's a kind of family resemblance, though, the options on the table for interpretations of quantum mechanics. And there's a core there. I mean, it involves Hilbert space representation, unitary time evolution, principle of superposition, representing properties in terms of Hermitian operators or equivalently orthonormal bases. And so there's a cluster of things that's shared among these approaches. And so I think we are on the track. I don't know what the next generation of quantum theories is going to look like. Again, if we did know those kinds of things, we just write it down. But I am confident that future general relativity will be grounded in quantum mechanical principles.
I agree.
So, I mean, one thing I want to say is that, I mean, it's not, I mean, okay, so the argument here is that the way I look at it, quantum mechanics or quantum theory is a framework for a variety of theories. General relativity is one very specific theory. I do agree with that, but it's not, I mean, it's not quite true. You can talk about framework, you can talk about theories that are a bit different from general relativity and satisfy similar principles. You can talk about sort of the general framework of differential geometric type theories that satisfy some of these theories, and some of these alternatives have been investigated. They indeed have been investigated, and alternatives to general relativity have been proposed. They've usually been ruled out. Not all of them have been completely ruled out, but there's a framework for things that are possible alternatives to general relativity, and there's an understanding of what kinds of evidence it takes to rule them out. Whereas, you see, the situation in quantum theory is much worse than that,
It's
which is
more difficult,
it's
not worse.
well, I mean, it's like
The stakes are
the range
higher.
the range of theories that are quantum-like, not exactly quantum mechanics, but quantum-like, is completely, you know, I mean, there are various frameworks for talking about it, but in terms of pushing them to the point where we can say, okay, here's the experiment where this one would make a different prediction from that one, and this is where we expect it to happen, is much less well explored than in the case of general relativity. In general relativity, there was a concerted program starting in the 1950s to try and experimentally determine whether this theory was really true, and so people really pushed the idea of these alternatives, and we haven't had that same degree of rigor in understanding this in quantum mechanics. So in a sense, to me, what you're saying seems precisely the wrong way around. Here we have unexplored territory in quantum mechanics, and in general relativity we have extremely well explored territory.
This is nobly said.
So this is this picks up an issue on something Sean said. I mean, you identify the technical problem. Quantum, if you try doing naive quantum field theory or general relativity, it's non-normalizable. For decades, we've cared that theory is non-normalizable.
Theory of everything should be realized.
Granted, yes, but theories that we don't think of theory of everything are perfectly
Right.
acceptable as well. The effective field theory of general, as I understand it, the effective quantum field theory of general relativity with a cutoff scale below the Planck scale, that theory is under tolerable control. We don't
Yes.
understand it nearly as well as we understand QED, don't understand it quite as well as we understand QCD or something, but we can calculate in it, we can get by in it. So, so sure, we have and it is irrelevant there that we have, it's not that we have a clash that's happened, this, contrary to how often it's shown in philosophy literature, it's not that we have a clash happening between principles of general relativity and principles of quantum mechanics that's irreconcilable at just the level of those theories themselves. We have a clash at Planck scale, sure, but there's a perfectly happy, peaceful coexistence between quantum general relativity and the quantum framework, perfectly happily at scales larger than Planck scale. And furthermore, if we decide, I mean, it's not like we have direct evidence for the quantum features of GR, but if we were to decide to give up on those features, then it seems that we need to modify quantum mechanics not at grand unification scales, but at the scales of maxed up objects. I mean, if you just this picks up something you said, Sean.
Yeah.
If we want to say how it is that I've got an ordinary decoherent type process whereby over the course of time Hyperion ends up in a decoherent superposition being this angle being this angle. If we try to put, for instance, the expected value of Hyperion's mass energy density into the Einstein equation, we will get empirically wrong results. So either we modify quantum mechanics so as to collapse the wave function, which is an honourable suggestion with some arguments in favour of it, but raises the stakes pretty dramatically, or we say we need to accept that there are superpositions of geometry happening at the scale of the Hyperion. I guess where this comes into the debate is I don't think we can say that if we want to modify quantum mechanics so as to hold on to those core features of general relativity, this is some statement about what happens in the far unexplored regimes beyond the LHC. It seems to be something we have to do at the scale of the solar system. And again, if you're a GWist, this is Christian nil. But you were saying that you didn't think we should modify quantum mechanics at that level. So I guess you could take this as a question to Matt. I guess how are we to think about gravity of the ordinary macroscopic situations in sort of decoherence classical chaos contexts. If we're not going to
So I deliberately didn't argue that I think gravity should be unquantized. I deliberately didn't argue that I think the theory in which you have a definite space-time with a definite metric tensor and was fundamental. I was rather making a different argument as to the principles of which theory are more reliable guides of theory building. So I totally agree with what you're saying. Of course, being somebody who's somewhat close to people who are trying to build quantum computers, I'm thoroughly believe in the idea that you can get an arbitrarily large system into a coherent macroscopic superposition, and once you're at that position and you think that you can have superpositions of mass on the on the at least mesoscopic scale, then the idea that gravity has quantum features is obviously true. So, but what I'm really arguing is when we try to construct the theory of quantum gravity, whatever that thing is, which theory's principles are going to be the more reliable guides to theory building.
But that pushes towards a peaceful coexistence, which is quite a nice way to debate. But I mean, if that's the sense we're talking about, if we're happy to include quantum general relativity as an aspect of general relativity, at that point we can say, okay, for all we know, maybe both of these theories are completely fundamental. Maybe the equivalence principle is an exact guide to nature, and also maybe quantum mechanics is that guide to nature.
But this isn't. I mean, I have to say, yeah, I agree that could happen, and I would be very happy if that happened. This isn't Sean's position, and it's also not the mainstream position in high energy physics these days. People who are taking like string theory based approaches, they also think that GR is essentially emergent.
Again,
I mean, I
this
think
is which
it's
feature of
fair.
GR, sure.
It's because quantum gravity is hard, and we have clues from things like black hole information that seem to be pointing us in a direction that says that at the deepest level, general relativity is not there. It's not really fundamental. It could be wrong, but that
Sure, yeah.
that yeah.
Well, I'm a little concerned. I feel like you guys aren't talking about the same sense of fundamental, but I mean, both of the senses in which you're discussing it are really interesting. Like Sean seems to be more concerned about like one theory being able to be derived maybe as from another in some way, and the other, Matt, you seem to be talking more about what's going to survive in a kind of future physics. I don't know if those, but I wanted to ask, Sean, when you were saying whatever interpretation of quantum mechanics turns out to be right, I still could win. I don't understand that for the epistemic view, because for the so you've got the psi epistemicist, so I understand him saying like, I'm not gonna say quantum mechanics is fundamental, whatever else they say, he's not gonna say that. So it's not, if you're psi epistemic, the quantum state is talking about something about us and our epistemic state. So it's hard for me to see how quantum mechanics can be fundamental if you're a psi epistemicist.
I guess the way I was thinking about it was more along the lines of, would some of the things we currently think about these theories need to be abandoned in this more fundamental theory? So I think that Matt is very, bravely says that he's actually imagining that when we try to solve problems like the hierarchy problem, grand unification, maybe the cosmological constant problem, quantum mechanics is really going to have to be modified from any of its current formulations.
Yeah.
And so I would include an epistemic version in that thing that would need to be modified. Is that fair, or are you Or is your epistemic
I mean,
view?
it's very easy for me to say these things, by the way, because I know next to nothing about these problems. So it's very easy for me to speculate that quantum mechanics might break.
Freedom.
Yeah. So if I, you know, I may at some point look in more detail into these things. It's not my research program right now, and I'm sure I will find very big problems with everything I've suggested. But nonetheless, I mean that's the proposal. Yeah.
I mean, to me, in quantum gravity, in the standard ways I can think about it, locality is not fundamental. Whereas in general relativity or even in quantum field theory, it is. So, in my view of how gravity will ultimately be quantized, this important feature of general relativity is going to have to go. And I take the important features of quantum mechanics, my version of quantum mechanics, to be there's a state in a Hilbert space that evolves unitarily, and everything else is emergent from that. And that will be exactly true in the ultimate theory, is my guess. So that's the sense in which I'm giving up on something from GR and not from quantum mechanics.
Well, for your whole package of views, I get it. It's just when you were like, but even if I had the epistemic interpretation, I just think it's, yeah.
Well, it depends what
But
replaces.
yeah.
Replaces.
Yeah.
Right.
Yeah.
I mean, I would say, I think Matt correctly says that we've had this program for decades now of modifying general relativity and testing it empirically in a way that we don't have an analogous program for quantum mechanics. I would suggest it's because quantum mechanics is, in some sense, very fragile. If you change it at all, it breaks immediately and is ruled out. And that is a feature of quantum mechanics. It's a good feature. General relativity is all loosey-goosey, some fields, and you write down some Lagrangian, and anything can happen. And why it's this particular thing, why there isn't some massless dilaton field, we don't know. There's all sorts of other things that could have been. Whereas quantum mechanics, like of all the theories ever, it seems to be that the fundamental framework of it is non-optional. Like here it is. There's Schrodinger's equation, and there's Hilbert space.
I mean,
So that's like
this I totally disagree with, because I mean I think that there definitely is a tradition of modifying quantum mechanics, and you might refer to the works on nonlinear Schrodinger equations and things like that, where you seem to show that as soon as you make a tiny change,
Right.
then all hell breaks loose. You get
That's
superluminal signaling and things like this. But this is because, I mean, it's not very polite to say,
Benighted
but
Everettians.
these modifications were done by people who were not particularly sophisticated on the meaning of the various terms in quantum theory. In particular, you know, if you list the axioms of quantum theory, I think the biggest lesson that we've learned from the foundations of quantum theory is that those mathematically independent axioms are not, in fact, physically independent, right? So you can't just go and change the dynamical equation without also changing the measurement postulates. It's inconsistent. And a lot of this generalization work has been done in not thinking about these things in a very sophisticated way. And you know, we've shown that in the last decades that in principle it's possible to have probabilistic frameworks which are more general than either classical or quantum. They exist. We don't know how to formulate real physical theories in them, but it's possible to do it in a way that doesn't violate no signaling and things like that.
I mean, that seems to be the sort of emollient common between there. I mean, what would be nice from what we're talking about, what we don't have is a way not just to say, here's a way you could change the abstract framework, but here's how you perturb the abstract framework, such as this is the perturbed version of QED.
Right,
Such that
exactly.
you can see how what effect this has on the moment of the electron or something.
Yeah, I mean, we don't even have much more basic things like that, such as how to, what's really a full understanding of the way to represent symmetry groups and this kind of thing. How do you represent time translation in general, and things like that. So this is not well understood, and it may be that all of these theories are complete bunk from that point of view. But of course, there may also be much more radical modifications of quantum theory that have to happen other than that. Like it could be that our most fundamental theory won't predict precise numerical probabilities, for instance. That's something that isn't usually on the table. Or you know, you can think of many other kinds of structures that we usually think of as just obviously having to be true, might not be. So I think there's a lot of scope there. There's maybe not a great physical reason for thinking that doing any of this will solve any specific one problem of I mean, the only one that there's any real motivation for is sort of discretization as a whole, and there's motivation for doing that coming from quantum gravity. But all I'm pointing out is that there is at least a large space of logically consistent possibilities that don't necessarily lead to pathologies that could potentially help to solve some of these problems. It's worth thinking about, and we haven't thought about it because the people who've been looking at these things aren't very sophisticated about quantum field theory, and the people who are quantum field theorists aren't sophisticated about this stuff. So there's a little bit of a culture gap there, but there's sort of no real reason not to try and push this forward.
Go ahead.
I just want to push back a bit on Matt's claim that we don't have as fundamental principles for quantum mechanics as we do for GR or hope to. So 2 examples I wanted to put out. So I'll agree. The fact that we have this workshop is an example that, of course, it's controversial, so not resolved. But being an optimist, at least 2 examples that I'd hope that we would converge on is some resolution around the gauge principle, which does a whole lot of work in theory building. When you want to talk about like a single principle that like unifies like why we have forces, does a whole lot of work. So you want to talk about it, you want to talk about a principle that's going to survive theory change. Gauge principle is way up there for me. And then the other thing I wanted to put up was, and I think we've said a bit about, was representation theory and just groups in general, which definitely play a big role in GR, but like, they play a unique role in quantum mechanics that's going to survive in a way I don't think we fully said as a group. Those are just 2 things that I would hope that we would clarify better.
I have to say I largely agree with you.
Yeah.
I mean, there is sort of push in some quarters to move away from symmetries and representations as being fundamental, but it is obviously one of the most successful programs in all of physics. And I think there's space to develop that beyond its specific application in the quantum mechanical framework.
It applies in classical physics.
Yes. Good. Yeah. That's.
I mean, in Matt's version of this, you could say, look, the question
That's right.
could be rephrased as which is more fundamental to quantum theory or the gauge principle. You could say, sure, we have quantum gauge theories, but if quantum theory fails, then somewhere between here and the Planck scale, between LHC and the Planck scale, will the gauge principle survive there? I mean, that could be asked. Gauge theories are the quantum theories, but that could be asked, at least the way you're pursuing the question.
It's not obvious to me the gauge principle will survive, but it is a candidate.
So I'm generally sympathetic with Sean's viewpoint here, although I have to admit it's partly because I don't know very much about modifications of quantum mechanics that don't break it. But it's something I should learn about. But I have a couple of reservations. One has to do with exactly what you mean by quantum mechanics or quantum theory surviving. I think that there are actually very good arguments that the Hilbert space picture is not going to survive, that come from these results of Torre and Varadarajan, that even if for a flat space-time free scalar field, that different choices of time slicing give you unitarily inequivalent Hilbert spaces. You can fit that all in what I would still call quantum mechanics, but in an algebraic framework and not a Hilbert space framework. So depending on which parts of quantum mechanics you're willing to give up and which parts you aren't, I think the answers might differ. The other thing is that it scares me to death to hear you say that you think that diffeomorphism invariance is going to be an approximate or an emergent symmetry, because without diffeomorphism invariance, you don't have the right degrees of freedom, and there's no sensible way to enforce to keep the graviton massless. As soon as you give up diffeomorphism invariance, it's equivalent to giving up gauge invariance in electromagnetism. Any perturbations would give you mass to the photon. Keeping it strictly massless, either diffeomorphism invariance is there, or something magical happens that somehow remarkably exactly reproduces the results of diffeomorphism invariance to arbitrarily high orders. And I just don't believe that. I think you run into
Yeah, I think-
Weinberg-Witten theorem and all sorts of
Well, I don't think you
stuff
run
like that.
into the Weinberg-Witten theorem, but it's because you've already done something worse, which is you discretized and have a finite-dimensional Hilbert space, so you don't
Okay.
have perfect Lorentz
Yeah.
invariance, so you don't have a Weinberg-Witten theorem.
Okay, yeah.
But still, you're right that getting things to be massless, whether they're photons or gravitons, seem miraculous from this point of view. The fact that you don't have easily phenomenologically noticeable violations of Lorentz invariance seems very surprising from this point of view. And that's why I always emphasize that this is the big looming problem in the whole program. I don't know how to get things like black hole entropy and de Sitter entropy right if I have an infinite number of degrees of freedom, which is the only way I know how to get special relativity exactly right. So something has to go. I don't think in either case it's quantum mechanics that has to go, but I think many people have been pushing on keeping diffeomorphism invariance and hoping the black holes in de Sitter space work out okay. It's worth some plucky minority of us pushing on the other possibility.
Yeah, okay. I won't argue with that.
Thanks. I thought that was really great. I've been thinking about this question for ages, and I'm completely neutral on what the
That's why you weren't invited to be on the page.
Yeah, I would have had to sit right between you. That's not true. And so my heart goes more with Matt, but just thinking of sort of, and again, these are very suggestive things, though. But you know, two considerations that I would invite you to think about. Whether one is, I mean, this is really anti-Matt, but my heart's with you. But the stress energy tensor, and again, this is sort of late evening sort of thing. I mean, it just seems so phenomenological. In the Einstein equation, I mean, it's just screaming out its phenomenologicalness. It doesn't seem like a sort of candidate to be the fundamental thing.
One side of my equation is marble, the other side is wood, or some
Yeah. So the wood is fundamental. It doesn't seem good. And then I was wondering whether it was useful to think about, any sort of particular experiments, particular cases that would sort of, be suggested one way rather than the other. And the one I was thinking of was the Cow experiments. So we have the neutron interferometers, and then the wave function picks up so the wave function then depends on the mass, and whether that, it seems to sit awkwardly with the sort of idea that the wave function would sort of float freely from the mass. And so I was just want to invite your thoughts about both of those things. The phenomenological.
I didn't understand the second thing at all. What is
the Cow experiments?
Yeah, what is your? Well, what about it?
Well, whether they are whether thinking about those lend support one way rather than the other. So there you have, in some sense, it's one of the,
it's a neutron moving in a gravitational field, right? It's not
Yeah.
quantum gravity.
What?
It's not quantum gravity.
No, of course it's not quantum
No,
gravity,
I think-
but it's
think
suggesting that the wave, that the mass is on the wave function.
Yeah, so the question is whether this implies some breaking of the principle of equivalence, because the
Oh.
wave function, the phase of the wave function is not independent of the mass, even though it's being picked up from.
I think the principle of equivalence is very overrated. It was a great way to be inspired to invent general relativity. At the end of the day, general relativity is the Einstein-Hilbert action plus some matter terms. And everything comes out of that. And so you just do that and you get the answer. Whatever the answer is consistent with what you've been doing.
It was supposed to be a
Makes me want
point.
to cry.
There's supposed to be a point in your favor that you're supposed to, riff off. But okay.
Well, maybe so much in my favor I can't even imagine it being wrong. I don't know. Yeah.
I'm not sure I fully followed the, what was this called? The experiment where you put a cow in superposition.
No, that's the
The
initials.
cat experiment.
Yeah.
So what's exactly the claim there that's
Can we make it more explicit, y'all?
The
I don't know either.
It's a neutron interferometry experiment in which the two paths move through a gravitational field at different heights.
okay.
So they pick up a phase
Different phase.
that depends on the gravitational field.
Okay.
So that demonstrates that the classical gravitational field does have an observable effect on the quantum behavior of neutrons. But the thing that people sometimes worry about is that the phase shift and therefore this quantum effect would be different if you do it with neutrons or hydrogen atoms, say. Depends on the mass.
Okay.
And there are claims that shows a violation of the equivalence principle.
That it shows a violation, or I mean, so I can
It's-
imagine that you say I know there are things that go along the lines of if you have a free electron and proton, they move in certain ways, and when you put them together to make a hydrogen atom, now there's binding energy, or there's a difference in binding energy, and the principle of equivalence would have that binding energy couple the same as any other energy to the gravitational field. Is that the kind of argument?
No, it's cruder than that.
It's sorry.
Go.
I was gonna say it's more that, I mean, there's I think it's the wrong construal, but there's a construal of the principle of equivalence that says, look, the way things behave in gravitational fields is completely independent of their mass.
Right.
So if the interference pattern of a neutron in the gravitational field is different from the interference pattern of an electron in the gravitational field, and there's a mass term in the interference fringes, which there is here, on that particular very crude conception of what the equivalence principle is, you've got a violation of the equivalence principle.
Okay, that seems crude, yeah.
Yeah.
To me, the correct equivalence principle is number one, I can choose coordinates in which the metric looks locally flat, and number two, there's no noticeable direct coupling to the Riemann tensor. So there's no difference very, very, very locally between special relativity and experiment.
The point wasn't supposed to be about attacking
You
the
were-
equivalence principle.
you were saying
It's supposed to be
something
about the
about
mass
mass.
dependence of the wave function.
Well,
That seems like mass is in the wave function. That
well,
maybe
I
this
mean,
was suggesting that
it definitely sort of. I mean,
the quantum
there,
first
there seems
picture.
to be. Okay, so as a psi epistemicist, I have to kind of make an objection here, which is like people tend to think that either there's the wave function, which in an interferometer spreads out along two paths, or there's not the wave function and there's a particle which goes one way or the other. But that's not a, you can still, even if you're a psi epistemicist, you can have that the ontological degrees of freedom are spread out. And in fact, if you want to reproduce interference, that's precisely what you have. It's just that those degrees of freedom aren't enough to reconstruct what the wave function is. So the idea that you get a different interference pattern depending on the mass, doesn't really bother me, because that mass, whatever it is, can be spread out along those two paths, and reproduce that apparent. I mean, I'm not bothered by that any more than I'm bothered by a usual Mach center interferometer, which I know how to reproduce in this kind of way.
That's more what I was getting at with it.
Adam?
Yeah. So I guess overall, I'm mostly, agreeing with Sean, but I want to agree with Matt. Sort of
Why does everyone
common-
agree with me and then reluctantly?
Well,
we like you better.
Well, because Sean, we learned it from you. We learned it from watching you. You said that you were sad that you couldn't be the bomb thrower.
Oh, that's true. Okay.
Yeah.
I guess my heart is with Matt too. then.
Well, so here's the thing. I mean, maybe this is just sort of like a crude restatement of what Matt's been saying, but the thing that I keep coming back to is, general relativity is a very nice theory. and it seems to work very well. We've thrown a lot at it, and it's, you know, sort of passed all those tests with, you know, style and aplomb. And then, you know, we have quantum physics, which, you know, works very well. Quantum mechanics works very well. It's passed, yes, it absolutely has, it absolutely has. But there's
We
this,
don't know why it's passed.
and there we go. There's this mess.
We don't
There's
agree
this-
on why.
Right, there's
We
this,
don't
there's
agree
this
on
mess in
why.
the theory, and there's this part of me that wants to say, why do we want to break the thing that works to make it more like the one that we don't understand?
Yeah,
That was basically
Yeah,
my
no, that's
first
sorry, yeah,
argument.
that's
Okay,
what
so
I'm
that's
saying.
basically
So-
right.
I can totally
Okay.
identify with
Right.
that.
Yeah.
Use the things.
Uh,
So I wanted to ask what's something from Sean's original comments, which was about the status of the Einstein field equations for Matt. So where do you see those going in the future? You talked about some principles of GR that you want to hold on to. What's going to happen to the Einstein field equation?
I don't know. I mean, I mean, I don't know what the final theory looks like, what mathematical framework it's formulated in. So exactly what happens to those, I don't know. I am fond of, well, I mean, this sort of comes from my affinity with some of the things that Ken likes to talk about as well. I am fond of thinking about the field equations as opposed to thinking about GR in terms of action principles, right? So I tend to think of, like, you know, the full theory with its warts and all as being what general relativity really is, including the solutions with closed time-like curves and things like that. I consider that to be part of general relativity. So I think thinking about the Einstein field equations is probably more in line with where I think the theory is going to go than thinking about the Einstein-Hilbert action, for instance. But other than that, I can't.
But you don't have thoughts on what's going to happen to the stress energy tensor on the right-hand side?
I mean, people like, so I sort of don't really understand this point about the marble versus wood business. Because it's like, are people concerned that F equals MA, that M is horrible or something? I mean, what's wrong with this? I mean, it's the thing that generates the you know, it's the source, right? It's the source term.
I quote you without agreeing. I suppose to push the line a little bit, we have very beautiful, clean descriptions of general relativity where the right-hand side is generated from the Lagrangians and matter field and everything's very beautiful. In the regime where we actually test and use general relativity, that's not specificity, it's very phenomenological, it's drawn from relatively strong, or relatively fuzzy principle. Again, this isn't my line, but that's the way.
Yeah,
I'm trying to
it's
do
some
it.
dust or something, right? So, sure.
It's interesting how little testing there is of the theoretically true Lagrangian Einstein equation plus fundamental plus matter field version of the theory.
Right. So the claim is that you would like a cleaner derivation of what that term is, as opposed to just saying it's whatever the stress energy tensor is. Yeah.
I mean, I think
Einstein exegesis, that's what I think he had in mind.
if you think of, as Matt doesn't want to do, general relativity is coming from an action principle, the niceness of the left-hand side is simply a reflection of there aren't that many scalar functions you can write down for the metric. There's just one at lowest order, right? And then it's pretty determined.
Well,
Whereas
more than that, it's super complicated. It's just that the other ones are normalized.
at first order, at lowest order, that's right, yes. Whereas there seems to be a lot more arbitrariness in Lagrangians you can write down on the right-hand side, which is okay, maybe, I don't know. But it's still, there is this mathematical operation I've learned where I can take one side of an equation and move it to the other side by subtraction. And so they're both on the same side, and they're both the functional derivatives back to the metric. I don't really see the difference between the two.
So, Matt, I am having trouble agreeing with you. You're not going far enough here. So you're right, Sean, that quantum mechanics is a tightly constructed puzzle. You can't take one piece of it out. It's gonna look bad. Just about every piece of that puzzle box, though, given what we know about the principles of GR, we really should have known better than to put that piece in the first place. We really should have known better to keep time separate from space and treat time as a separate thing. Given what we know about space-time, we really should have known better to talk about states on instantaneous surfaces. We should have known better to talk about operators operating on those states on instantaneous surfaces. We should have known better to go back to the original motivation of the Schrodinger equation, which was took two things. It took the Hamilton-Jacobi action, which doesn't live on a state. It's an integral, and it's an integral to the point that is now, assuming that you measure it there, and then you compact all that and say, there's my state. Even though if you don't measure it there, it goes on and that wasn't the action at all. We should have known better than to go to configuration space from StatMech, which we knew was not a real thing, and say, this is the framework of the theory, when we can clearly see where Schrodinger stole it from StatMech. It was obviously an epistatic construct. It was obviously encoding correlations. And so we took all these things that we should have known better to put them together, and now we have this tightly constructed puzzle box, and sure enough, you take one of them out, and it all falls apart. But it seems to me that, given what we know, it looks kind of ugly.
So we should have known better that we should have used path integrals or Heisenberg picture, but that is what we do.
Okay, so then we could talk about the path integral. We could talk about is there an alternate way without any of the states, without any of the operators, to make sense of it from the path integral? And sure enough, it is, and that's where our best successes come from. That's where our best matches to data come from, is from the path. What the Schrodinger equation gives us is probabilities that we've dumbed down into thinking it's a good prediction, when it's actually giving us probabilities, but it's not actually giving us.
Quite good predictions.
Well, they didn't used to be considered good predictions to predict a probability. Now we consider it a good prediction.
But I think you're talking very historically about where we borrow things
yes,
from.
exactly.
But I think that you're then doing disservice to the final product, which, regardless of the Frankensteinian way in which it was assembled, is not actually a bunch of different pieces fit together. It's a quite compact, sleek, mean machine of the Schrodinger equation acting on vectors in Hilbert space. And it's hard to mess with it. And I would further say, in the GR versus quantum mechanics thing, we haven't even mentioned the word singularities yet.
Yes.
And one problem with all of classical mechanics is enormously more complicated than quantum mechanics is, because quantum mechanics is linear. So in classical mechanics, you can run into singularities at the boundary of configuration space. In quantum mechanics, h psi equals id by dt psi. And if you think of it the way I want to think of it, as you're a vector in Hilbert space with a Hamiltonian, right psi in the energy eigenbasis, and all that ever happens in quantum mechanical evolution is the phase of every little energy eigenstate rotates. So all of your evolution, no matter how complicated your system is moving on a straight line in a little torus. And it will never end. It will go on forever. It's immediate, and it's pretty, and there's no singularities, and everything is great. And you guys want to give up on that. I don't know about these people.
That
Well,
seems to be.
and then you measure it, and that's not what you see.
Sean, that seems too quick. I mean, I could do probability distributions on classical mechanics, and I could use the Liouville equation, and that's just as linear as the Schrodinger equation. But I can't move the singularities in classical mechanics that way. I mean, yeah, I
No,
agree
because
the
some-
singularities go away, but it's not simply linearity.
But that's because if you feel Hilbert space in your bones, you do not think of it as a set of square integrable functions of configurations. You think of it as a vector that's doing something. And so that classical probability distribution is necessarily probability distribution on classical things that could go singular. Whereas the quantum vector is just moving around in a little circle. It's much nicer.
It's the most beautiful thing.
Yeah.
But
Yeah.
you need operators too, don't you?
Well, I think all that emerges. That's a longer conversation. But
Yeah, okay, so rather than engaging with that, if you want to fight, you can.
Okay.
Yeah. So.
That was said as a.
Yeah.
Somebody fight.
Would you two like to take over the
Yeah, use the bench.
No, because I'm gonna win and then I want to say, first of all, I think neutral causality is an interesting program. I think it's an interesting program. I have some sympathy for it, but I think that your historical argument there was misguided, because you could say the same thing about almost any physical theory in the history of science. You know, I mean, look at Newton's inspirations for coming up with classical mechanics. He was, you know, a magpie. He picked things up from, you know, all sorts of strange places, and it shouldn't have worked. You know, I mean, he was, you know, people called him like the last alchemist or the last magician, and they were right to do it. I'm not gonna bash classical mechanics because, you know, he picked up, you know, weird shit from all sorts of places, and he decided, you know, no, I'm gonna say, you know, I'm gonna be crazy. I'm gonna say that both, you know, something proportional to b squared is conserved, and something proportional to b is also conserved, and we're gonna give them different names. Like, you know, that was a perfectly reasonable move.
Okay, well,
Yeah.
let's talk, we're not debating Newtonian, we're debating.
Yeah, I know, but what I'm saying is that you know, that attack of, you know, oh, it was all these things that we should have known better to put together into one thing, and now it's this tightly constructed puzzle box, that's theory.
If you don't like
Bit
philosophy
history.
science, context of discovery versus context of justification.
Right, yeah, there we go.
And you're just in the history of science is whitewashed.
Yeah.
Or at least in a way that he was trying to recount.
Yeah. I mean, I think, well, I mean, of course I'm gonna say this, because, like, this is
The good old
what I
days
do,
were
but-
messy too.
Yeah, exactly, it's always messy.
So this is a fun conversation that is wandering away.
Yes.
I move that we stop the video and declare victory, and then gather around and have more drinks and talk more.
I
We're going to declare
at least won the hearts.
And I will take the mind.
I would say I'm enthusiastically and complacently pro quantum mechanics. I do feel.
Yes, and happily.
I took the heart.